Let us begin. Welcome to BIMSA. Welcome to the workshop in mathematics and mathematical physics. And
Hi, good morning. This is Yao.
wait, wait. This will wait a second. It's a video recording. Okay. So I want to introduce Professor Nikolai Reshetikhin and ask him to formally open the workshop.
Thank you. So it's my honor to do this, and to open the workshop, I want to present Professor Yao's address. So please, Professor Yao.
Hi, good morning. This is Yao. I'm the director of BIMSA. Welcome you to come here for this great conference, Mathematics and Mathematical Physics. Well, of course, it's a field that I always fond of. I spent my whole life on understanding mathematics and physics, how they interact. And I'm glad that you're doing it here. And I wish you success, of course. And I'm very glad that many distinguished mathematicians come here, including Andrew Okunkov and many others. And I'm very happy that Pension has been working very hard on this workshop, and also Tom and several other good people. And I think such an interaction should continue in BIMSA and also with Tsinghua University. And it's very important that we learn from each other and also teach our students who may not know that well about what happened in the last few years or last 30 years. The more interaction, the better it is. Especially now that our students are graduating and getting into PhD or finish their PhD, this kind of workshop will be extremely useful and make them learn what is going on in the modern world. So I hope you continue to interact and also continue this kind of workshop each year. Congratulations again. Thank you. Hi, good morning. This is Yao. I'm the director.
So Professor Yao was instrumental in this project. Basically, it was his idea, and kind of his energy resulted with the help of many others in implementation of this institute. So this is the first time we have this school, and I'm sure it will be a success. Anton Jamai is kind of organizing every detail very successfully so far, and let's hope it will be the same way. So I'm sure you will learn about BIMSA, you will learn about this neighborhood, you will learn about Tsinghua University if you don't know about this. So I don't think it's time for me now to explain this. It's just all I can do is I wish success to this workshop. Yes, and Anton is helping me because I would not forget it, but I may have forgotten it to say now because it's a very exciting moment. So this school is dedicated to the memory of Igor Krichever, who whose fundamental contributions at the interface of mathematics and physics, will be remembered for many years and are part of the history of mathematical physics. So you seen that the talks will be many. I mean, the subject of the conference is integrable systems and so on. So I just want to start. Thank you.
Okay. a few quick organizational remarks. We will have a tour of the Great Wall on Wednesday afternoon. BIMSA will organize shuttle buses to go there, but unfortunately you have to buy your own tickets. If you just want to enter and walk to the top of the wall, which is not recommended in Wednesday's weather, it's I think 45 yuan, and if you do a reasonable thing and take a cable car to the top, I think the full ticket is about 200 yuan. Okay, but we will have the buses. The buses will leave from here, take you to the wall, and bring you back for dinner. Then also we will have a banquet on Tuesday of next week, and Saturday of this week is a free day, and probably is a good idea to explore central Beijing and various attractions there. However, if you want to stay here and work and study, which would be a good idea, we will feed you. Okay, so it will be something in between lunch and dinner, just a big meal in the afternoon. Okay, why am I saying all this? Because you need to sign up for all three things. Okay, we need to know how many shuttle buses do we need to get you to the wall. We need to know how many people are coming to the banquet. We need to know how much food to order for Saturday. Okay, if you go to the conference webpage, there is a link, and there are 3 forms that you fill, and the deadline to fill these forms is by the end of the day today. They will disappear past midnight, and any requests for late additions will be ignored. Okay, so please, if you're interested, fill in these forms. Okay. And if you have any questions, ask me, ask other organizers, ask people who wear this red name tags. And Kolya, I think you can introduce the first speaker and we'll get going. Thank you everyone for coming and welcome to BIMSA.
Okay, so first I forgot to say that the reason why Professor Yao is not here, Andrei Kunkov is not here, they are attending the meeting of the Chinese Academy of Sciences. So Andrei will come very soon. So it's my pleasure to introduce the first speaker, Sam Grushevsky, Integrable Systems Approach to the Schottky Problem and Related Questions. So let's...
Testing. Can you hear me? Yes, good. So it works. No. No. I still have 3 minutes, so take your time. Yeah, I mean, I'll start in a minute. Okay. Shall we begin? So First of all, thank you so much to the organizers for organizing this and for inviting me. It's my pleasure to be in BIMSA for the first time in my life, not the first time in the Beijing area. So I'm going to talk about integrable systems and algebraic geometry. There's a slightly different title, but never mind that. So there will be two motivations. One sort of comes very naively, and I don't know whether you can read this in the back. Can you read this on the screens or somewhere? Well, you can read on the screens on the side. Okay. So first is I want to tell you how to solving differential equations. This is a very naive viewpoint. Of course, it will become slightly less naive as we go along. So this is well known for linear differential equations. So if I have a differential equation, so u is a function of x, and I can try to solve an equation, u prime plus 2u is equal to 0. We all know how to solve such things. If I write a higher order equation, u, a number of derivatives plus, 5u and something like that, you also know how to solve that. But what if nonlinear? By nonlinear, I don't mean that it's nonlinear in the derivatives, but I just have coefficients of functions. Of x. So what could you do then? In your ordinary differential equations, you probably learned something, but maybe not as much. And this is a very vague question, but presumably quite interesting. And when you ask such a question, you need to ask, what does it mean to solve? Why should you ask this? Because if you're trying to solve something like that, well, you're going to get various exponentials and stuff like that. These are elementary functions. I know very well how to solve for them. But in general, if I write a complicated differential equation, there is no reason to think that this will have a nice solution. So certainly, this is not going to be an elementary functions. And if you want to convince yourself of that, just think of the gamma function. It satisfies some differential equation under certain circumstances. But you can think about hypergeometric functions and so on. Well, I wrote diff dot, and you can read it any way you want. This was by accident. I was going to say in 2 minutes that I'm not going to treat difference equations. So let me wait for this 2 minutes. So, but you should know that when you try to solve, sometimes it could be that the best way to describe a function is to say it is a solution of such and such differential equation. And you may not necessarily hope to get any better view of this function. So here, solve would mean that you can get some more information about what this function is, instead of just saying it solves a differential equation. Which is to say, you may want to construct this function. So of course, hypergeometric functions or gamma functions, which satisfy difference equations, appear in other situations, not just the solutions of differential equations. They appear in nature in a way. And sometimes you may have systems of differential equations. This is all motivational, so I'm not aiming for any precision whatsoever. And this sometimes may be completely integrable, which is to say that even though you maybe don't know how to solve, you may know all the integrals of motion somehow. Okay. And then there is something that this is going to lead us to, and this is to be an algebraic solutions, by which I mean some solutions that come from algebraic geometry that can be constructed from some geometric data. You can think about whether these fit in this category. That depends on your viewpoint. And the main works I'm going to describe here are the works by Igor Krichever, and they're basically in the 70s. The foundations for what this is going to be is from the 70s. So that's motivation number one. There is motivation number two, which is about curves. So for me, a curve throughout these lectures will be a complex, projective, which is to say algebraic and compact, connected, reduced, you didn't hear these words, which is also the same as a compact Riemann surface. Okay. If you have a curve, there is lots of geometric data associated to this. One particular kind of interesting geometric data is a Jacobian of a curve, which I'll denote Jacobian of C. And you can embed a curve inside this Jacobian. So what is a Jacobian? Jacobian is a principally polarized abelian variety. I'll explain what these are in due course. And the map that takes a curve C and sends it to its Jacobian defines an embedding of the moduli space of curves of genus G to the moduli space of principally polarized abelian varieties of genus G. These are moduli spaces. And this is a very interesting map for the following reason. Somehow I would view moduli of curves as a very geometric object, a very complex geometric, algebraic geometric, depending on your viewpoint. But this is a geometric thing. So somehow geometry, there are objects on curves with a geometric nature. This is in some sense a more arithmetic object because all abelian varieties are quotients of the complex space. And somehow the data is more of an arithmetic nature. It's some lattice of something. So this relates to different kinds of data. And there is a problem. Let's call this map J. The problem is called the Schottky problem. It's about 150 years old. And this is to describe the image, to find out which abelian varieties are Jacobians of curves. Okay? So from now on, when I say curve, I always mean compact, smooth, all of that. Whenever I say abelian variety, I mean principally polarized, just because it's faster for me to speak this way. Nothing else will appear in this lectures until further notice. And here, there is this Schottky problem, which is to describe the image. There is a weaker problem, a weaker version of the problem. So you see, if I have a curve, I can embed this curve in its Jacobian. So given a curve C embedded into an abelian variety, you can ask whether the abelian variety is the Jacobian of a curve. That's a much weaker version because this somehow says if I give you an abelian variety, can you find a curve such that this abelian variety is a Jacobian of this curve? This says if I give you an abelian variety and somehow magically I also give you a curve sitting inside this abelian variety, a specific curve, not some curve, is the abelian variety the Jacobian of this curve? This is a much weaker question, right? I have given you much more data. You can try to think about this question. It's still highly non-trivial and interesting things do happen. We won't go this way. And what relates these two approaches is somehow the keystone. I don't know whether keystone is the right word here. Is we're going to solve suitable differential equations via some functions. I mean, the solutions will be given some functions which originate from curves. And the differential equations will be, that will solve these differential equations will solve the Schottky problem. So this is why these two stories are on the same blackboard, because if I solve, well, I'll tell you precisely what the equations are, how we'll solve them, what the functions are. But the idea is somehow, starting from a curve, I'll be able to construct some solutions of some differential equation. And the fact that I have been able to do this will characterize curves among all abelian varieties, which means you could try to do similar things starting from an abelian variety, and you will succeed if and only if this abelian variety is a Jacobian. The main result, is somehow the most striking celebrated result here, is perhaps Krzyzew's proof about 15 years ago now of Welter's trisecant conjecture, characterizing abelian varieties, Jacobians among abelian varieties by the property of the Kuma variety having trisecants. I will not aim to prove this full. I'll prove a slightly weaker version more or less completely if we're successful. But we're not yet in a position where I can explain what these words mean, and it will take us quite a while to get into that position. Okay? So that's roughly the plan of the lectures. Okay, now being a good American professor, comes time for disclaimers. So I'm not an expert on integrable systems. Many people in the audience are, and probably know many parts of the theory better than I do. So if I say something completely wrong, please correct me. If I am lying slightly, I will happily admit that I'm lying slightly. I will lie throughout. So I will try to avoid as many technicalities as possible. Hopefully, I will not write things which are just false on the blackboard, but I will write things purposefully which will need more work to make them precisely correct. Okay? I also do not know what your background is, so maybe this is a good time to find out. How many of you think of yourselves as primarily experts in integrable systems? Raise your hand. Don't be shy. You can be an expert in more than one thing. How many of you think of yourselves as algebraic geometers? How many of you think of yourselves as complex geometers? Differential geometers? Representation theory? Algebra more broadly? Mathematical physics? Okay. I'll keep asking this because I would like to know at which speed I should go and what I should cover in more detail. So please ask many questions. This would be wonderful. Also, if I'm going too slowly, just yawn very loudly, and I'll get an idea that I should speed up. But basically, we'll see how fast it goes. There is something I do want to cover, but on the other hand, we can cover less or more depending on how it goes. Any questions on the motivation so far? Okay, now we'll be much more precise. So I want to talk today about commuting differential operators. Okay, so last check. Is this large enough about convergence in any shape or form? Okay. So this would be called a solution that's normalized at x naught. Notice, of course, this condition does not depend on x naught. This is just to say that I want to take, at lowest order, I'm just taking e to the k times x minus x naught. And then I want no corrections at higher orders at the point x naught. Okay, let's prove this. Maybe before I do this, is the statement clear? This is a purely formal statement that says, if I give you any differential operator L, which is to say, if I give you a bunch of these UIs, and of course I will from now on always pretend that they are of this form, that I can find unique functions psi s, this is my badly written s, right, such that this series in K inverse, right, this is a series in K inverse, well, times exponentials, but never mind that, solve the equation. Well, the proof is very simple, so it's just a computation. So what are we looking for? So I want my psi to be equal to the e to the k times x minus x naught, right? And I want the first order term to be 1. Then I want psi 1 of x k inverse plus psi 2 of x k minus 2, right? That's what I want my psi to look like. And I want all of those guys to vanish identically at x naught. And I just differentiate. So I'm going to compute more or less for you the derivative of this, the i's derivative. And let me just compute the i's derivative of this term. So x, right? So I'm going to get k to the minus s if I differentiate many times here. Sorry, there is, I'm forgetting the exponential, which of course is here. So notice what's going to happen. If I differentiate, the exponential is not going anywhere, right? It's going to stay. If I differentiate the exponential with respect to x, I'm going to get a factor of k, which is going to cancel one of the k's from here. If I differentiate here, the powers of k go whatever down. Sorry, if I differentiate with respect to k, which we're not doing yet, but we'll do in a second, the powers would go down. But this is a constant. It doesn't play any role. I'm differentiating with respect to x. So I get k to the minus s times, well, d psi s di dx to the I, e to the k, e to the k x minus x naught. That's one thing I could do. Or I can differentiate one time less, di minus 1. And then I get times k for differentiating the exponential, plus, and so on. For me, all the combinatorial factors are 1. So if you keep going, maybe there are some factorials, but let's not worry about it. So what this is to say is that if I differentiate this term, I'm going to get k to the minus s times something that doesn't involve k plus something times k plus a polynomial in k of degree whatever it is, s minus 1, I guess. Okay, so that's what I'm going to get. So now if I take the derivative of psi, I will take such a derivative in each term. So I apply i's derivative to here. I'm going to get a term in the lowest order plus the next highest order plus so on, right? So what you can do is you can just, so you simply solve. So so at each order, at each exponent of, at each order k to the minus s, you solve for the next psi s, right? So the psi s will start contributing from the order minus s and higher orders. And the first time it shows up, it will start canceling some of the things we have before. So you can just solve for it. Of course, to solve for it, you need to solve a differential equation which says some derivative of psi is equal to what is given. And I'm not going to do this explicitly, but this is going to work, right? You can always integrate. That's it. And notice that somehow, if you were to write this, this will be some kind of diagonal, triangular matrix of equations, and each psi will show up in exactly one term first, so you solve for that. As the next order, you'll have one more derivative, but then you'll go to the psi x plus 1. So this will keep going. So exercise is to do this. Exercise, which I encourage you to do this, is to do this completely, correctly, by yourself. So somehow, as you may notice, this is completely elementary, right? I haven't done any higher mathematics whatsoever. And much of my course will remain completely elementary. And I know from experience that if somebody says, oh, this is elementary, many people, especially advanced PhD students, just put down their pens and think, oh, it's elementary, it's not interesting. So many years ago, I went to a course on analytic number theory taught by Peter Sarnak. And I don't remember what the result was, but this was in Princeton, and there are many very advanced PhD students. And Peter said, oh, and now let me tell you something elementary. And you could just hear all the students putting down their pens because it's elementary, they're not going to take notes. And then Peter Sarnak looked around the room and said, no, I didn't say trivial, I said elementary, which means there is a very nice idea there, which doesn't require any presupposition. So I think there are many nice ideas, many due to Igor Kirchner and what happens here, but they are elementary. So I do want to ask you to do this. Just convince yourself that this is just a computation. There is nothing mysterious. If I do it on the blackboard, I'm sure I'll mess up. But if you do it on a piece of paper, you will probably succeed. Okay, so that was my end of the proof. So raise your hand if this is believable. Okay, raise your hand if you're planning to do the exercise and do it correctly. The answer to that question was mandatory yes. Okay, corollary. I mean, this is not quite a corollary, you need some more work. But, oh, I'm sorry, I didn't specify the time. Yes, so you may, if you have already done this in the past and remember how it worked, then you're fine. Yeah. Okay. I will denote this solution. I will need to denote this. So denote. So I get this solution. I'm going to denote this as psi, which is, of course, a function of x. And I'd like to keep k as somehow an argument of this function because it's a series on k. It depends on k, it depends on the eigenvalue. And of course, it's normalized. So let me put x naught here as the point where I've normalized. So this is my notation for this solution. And notice something interesting happened here. Elementary, but very interesting. Before, I was saying this is a function psi of x, right? Which is an eigenfunction of L for the value k. Somehow a leap of faith here is I'm now considering psi, as a function of x and k. Yeah, it's a formal function, it's a formal power series. I'm not worrying about any kind of convergence. But notice what is being said here is I didn't say anything about what k is, right? So this was a true statement for any k. And I have found a solution for any k. And this solution, you see exactly how it depends on k. I'm not going to get into the discussion of whether you can sum such formal series. That's not the point. But the point is that this has a very explicit dependence on k, which is essential. So somehow, instead of just solving for one eigenfunction, I have solved for all eigenfunctions at once for all k. And what is interesting is that I can see specifically and very explicitly the dependence of all this on k. So notice what is happening here. Instead, if you're doing linear algebra in a finite dimensional space, you have a finite number of eigenvectors, right? For each one, you have a finite number of eigenvalues. For each one, you have some eigenspace of solutions, which is finite dimensional. So you have your 5 eigenvectors, whatever. Here, the eigenvalues can deform arbitrarily, and the solutions will deform nicely if I deform the eigenvalue. This is crucial to the whole story. No, sure, yeah, sorry. Sorry, I mean, the ASIC, yes, okay. So you want to basically, you start with the exponential, and then all the corrections should not touch your value at x0, okay? And what you can prove here is the following, is any formal solution of my equation for the eigenvectors has the form psi of x k is equal to this chosen solution times some function which only depends on k and x naught. Okay? So I found one solution. That was a normalized at x naught solution. I claim that I have found all eigenfunctions, essentially. That everything else, I know how it works. I just take this guy and I multiply it by something which is independent of x, right? This is independent of x, but it depends on k and x naught. We can discuss how it depends on k and x naught. I'm not going to go into that. I mean, but you can see this. How do you prove this? Well, you need to prove uniqueness, right? You need to, obviously, what I have written here on the right is going to solve this equation because L is a differential operator in x. From the point of view of x, this is just a constant. Nothing happened. Okay? But you need to check that there are no other solutions. This is trivial, and this is your exercise. Prove this. Okay? Again, this is an elementary exercise, but I highly encourage you to do this just to see that things just work very naively. I mean, I don't know naively, but very directly. Okay. So this sort of completes the study of eigenfunctions, formal eigenfunctions of one differential operator. What I'd like to do now is to consider more than one differential operator. So I have my L, which was L1, which had this form that I was writing on the blackboard for you. But I could also consider another differential operator of the same form. Yes. No. Whenever I make a mistake today, I'll blame jet lag. It will get harder as we go along. But yes, thank you. This certainly had coefficients. And okay. And I can have another differential equation of a different order, a differential operator, but of the same form. Okay. I know the eigenfunctions of this one, the formal eigenfunctions. I can do the same analysis for the eigenfunctions of this one, right? Doesn't matter. There is some technicality here that, for me, technicality, which I'll try to avoid mentioning, but whenever I do this, I'm going to assume an M coprime. And the main example will be n equal to 2, m equal to 3. Some of the things I write will implicitly assume this, but I won't go there. That's technical. So I have two such equations. I can find all the eigenfunctions of this guy. I can find all the eigenfunctions of this guy. If you think about finite dimensional linear algebra, if I have two linear operators, when do they have a common eigenfunction? So if I have two matrices, yeah, so now we have to be careful. Do I want them to have one common eigenfunction, or do I want them to have all eigenfunctions in common, right? And this becomes even more interesting in my infinite dimensional spaces. So I'd like for them to have all eigenfunctions in common, which is to say they would commute. So the commutator is, of course, so somehow the moral question is, when is the commutator L1, L2 equal to 0? Okay? So exercise is to write down what this means explicitly. Write down this explicitly for n equal 2, m equals 3. So just do a computation. Commute two differential operators. Don't be afraid. You'll compute some derivatives of v. You'll compute some derivatives of u. You'll get something. This is some condition. If you look at this, you can first of all, ask yourself what's the order of this differential operator, and then all the coefficients beta vanish. So this, even though it looks like one equation that I wrote here, this is more than one equation. And if L1 and L2 were of very high order, these are many, many equations relating U and V somehow, right? And I'm asking you to really compute this in the simplest case, n equal to m is equal to 3, which is actually good enough for most of our purposes. Okay, next theorem. So given L1 and the corresponding solutions psi, normalized solutions x, k, x naught, then for L2 of the form as above, L1, L2, L1, L2, the commutator is 0, if and only if I take L2 and apply it to my solution, normalized as normalized, and then I divide by psi, is a function which I'll denote A of k. So the key point here is that this is independent of x naught. Okay? Proof. This is again an elementary computation. Before I do this, I'm being very sloppy where we work. These are all formal solutions. Until further notice, until we start doing geometric construction of solutions, psi are just formal expansions of this sort, right? And they all start with 1, so I can reasonably invert them. That's not an issue, right? And this is only formal. I can compute these things. They will not converge, but I never worry about convergence. But I can compute term by term exactly what this means, right? And in principle, this is going to depend on x naught. First of all, let's convince ourselves it does not depend on x, right? Because somehow I wrote some function of x, k, and x naught. And why does it not depend on x? Well, it doesn't depend on x because of this, right? So proof, I don't know, one of the two directions. If L1, L2 is 0, then of course L2 psi xk x naught is also k to the n eigenfunction of L1, right? Just because, you know, L1, L2 psi xk x naught is, if they commute, the same as L2, L1 xk x naught, which is L2 times k to the n psi xk x naught, right? This is the usual thing. I mean, this is why in finite dimensional linear algebra, commutation is the same as having a common basis of eigenfunctions. That's trivial, right? But this means, so by corollary, that I'm going to use, even though of course I haven't proven this, but it's straightforward and that's your exercise. This means that my L2 psi xk x naught must be equal to psi xk x naught times something which is called A of k and x naught, right? So that's automatic. So I know that if the commutator, I'm proving this direction, right? If the commutator is 0, then I know that L2 psi is an eigenfunction of L1. So it's this times something which is independent of x. So my goal now is to show that it's also independent of x naught, right? And I'll write something, and then I'll hope that you just believe me. Okay. I want to be sure I write correct formulas, which means I will. So I want to check that this A of k and x naught is really independent of x naught. So I just like to compare A of k x naught to A of k and some other thing, some other value. So for any x naught prime, I can also, of course, compute that L2 psi xk x naught prime is equal to psi xk x naught prime times A k x naught prime. And then what I want to know that this is the same as for x naught. Okay? And for this, I just do a computation and think about what this means.
But I think it already followed from what you said. Because what this corollary means that psi of xk x naught depends on x naught only by scalar. Independent of x. So the ratio doesn't depend on x naught at all.
The ratio of what?
L2 psi over psi.
Why?
Well, because psi different x naught and x naught prime differs by a constant factor, which is independent of x.
Yeah, but which differs on x naught and so if I take, there'll be a ratio of these two things, yes?
So if you change x naught, the sign changes by overall scale.
Yes.
So L2 psi over psi doesn't change.
Yes, okay. So, yes, I want to write something which is equivalent to what you're saying. I want to write something else. Yes? I was very sloppy always. So I hope that A, in all of this, I hope that A has this, A is going to be a formal function always. I cannot hope for any better. A is not going to depend on roots of k. It's going to depend on k itself, right? That's why I'm using k and not e, which is n's power of. And this is going to be a formal function which I can expand in a similar form. I'm being... At the moment, I'm talking about formal solutions. What I'm doing now is completely formal. There is no curve. There is no convergence. There is no actual function. It's just a formal sums of, it's an exponential times some formal series. There is nothing like that, but yes. So, of course, what Pasha said was completely right, but I want to somehow say that there is an easy way to see this. So, if I take psi of x, k, x naught, and then take e to the k x naught prime minus x naught, right? This, is just a constant multiple of that guy, right? But how did I change it? Well, this was, the psi was basically e to the k x. Now I have to suffer because maybe it's this way, okay? Plus psi 1, psi 1 of x, e to the k x minus x naught plus dot dot dot, right? Times e to the k times k to the minus 1. Okay? So if I just recompute this, the exponent just got changed, right? So nothing much happened. Right? So this is also an eigenfunction of psi, but now it's normalized at x naught prime. True? What was the normalization? The normalization was that this guy was supposed to vanish at x naught. It still vanishes at x naught. I didn't change that, right? So this is not the normalized. So this is not equal to this in general, right? But it's still a solution. And this means that this guy must be equal to my original function times some b, say of k, x naught prime. X naught depends on x naught prime. Okay? But this dependence is very easy, and I know how it works. So you can compute then that this implies what Pasha was saying also. But what I wanted to do, I wanted to do this computation. Somehow the dependence of the normalized solution on x naught prime on x naught is not so immediately obvious. It's not just you multiply by an exponential. It's a bit more elaborate. Okay? So, you know, compare a k x naught prime, and you basically multiply L2 by the same. So L2 will multiply the same way if you want to switch. And B, and you're going to get that A of k. Okay. So as you probably have figured out by now, if I'm being so sloppy, this means it's your exercise. So
There exists unique solution, formal solution up to scaling by series in K.
we could say it many ways, but
Every point x0 defines the normalization.
every point x0 defines a normalization. Passing from one normalization to another is some procedure. And then the normalization for L2 psi will change the same way. And this is what this says. This is exactly what this says. So you are going to compare here psi xk at x naught, the same at x naught prime, and the values of this. And this you are going to change in a trivial way. So this b, if I put L2 here, is going to be the same. But this means that this rescaling is just the same. So it all cancels. Okay? Make sense? But please complete this. Of course, I lost my eraser. Okay, so this was one direction. The other direction, I haven't done proving the theorem. I haven't finished proving the theorem. Is I need to show that if L2 psi divided by psi is a function of just k, then the commutator is 0. Okay? So this is also somehow easy, but elementary in perhaps a different way. So what do I mean by that? So how do we prove this? So I know something about eigenfunctions, and I want to prove that the commutator is 0. This is a trick. I mean, this is an easy mental exercise that we're going to do a couple times. So what is this commutator? This commutator is a differential operator of some order, you know, n plus m minus 1 or whatever. And I want to know that this is a 0 differential operator. If I have a differential operator of finite order, and I fix its eigenvalue, k to the n here, then the space of solutions is going to be finite dimensional, right? Because I can just solve term by term carefully. But I also know how the solutions depend on k. So if I find this differential operator that somehow has an infinite set of solutions, it must be identically 0, right? That's what we're doing. So let's just see what happens. So I want to check that this commutator will kill all of these functions, right? So there's something else I want to say. Sorry, 1 second. Questions? Hmm? All right, there is nothing else. So let's just compute. So this, of course, means that L1, L2 psi k x naught is going to equal to L1 applied to A of k, which is a constant, L2 psi xk x naught, right? Which, of course, is the same as to say this is A of k, which is a constant, does not depend on x naught, times k to the n psi xk x naught, right? And this is true for any x naught. So L1, L2 has an infinite dimensional kernel Let's do this for all x naught. So L1, L2 is identically equal to 0.
Wait, I mean, you have to show that they're linearly dependent, actually, right?
Yes, but since I know how they are normalized.
I mean, you need to vary k to have a
Oh, sorry. For any k and x naught, sorry. No, sorry.
and also, formally speaking, you need to say something because you cannot specialize k because the solution is formal.
Yeah.
You do it, but it requires a little bit.
I don't think I need to say that because the solution is formal, but there is still a finite dimensional space of formal solutions, so I don't care. I don't think there is any difference to that. So the solutions dependent on k, and there will be an infinite dimensional space of them because for different k's I get different solutions, but that's all.
You cannot specialize k formally because of the formal nature of the
You didn't hear that. No, I mean, we can talk. Okay. I'll pretend that I've proven this because I'm not bothering with.
So it is easy for my question to I'm not saying it.
I know, but I don't. I want to pretend it's okay. Okay. So what does this tell us? This tells us that somehow, given a fixed differential operator L1, I can find out if some other differential operator commutes with it by checking how L2 acts on the eigenspaces of L1, right? That's what this says. Now you can ask, what if I have L1, L2 equal to 0, but also L1 and some L3 are equal to 0? Okay? So this means that both L1 and L2 must satisfy the condition that is written here. But then I claim, corollary, and this is true, then also L2 and L3 is equal to 0. Okay? This is now very easy because what does this mean? So this means that for any psi xk x naught, this is a solution, eigen function for x1, or for L1. I know that L2 psi is equal to some A2 maybe, of k. And I know that L3 psi psi xk x naught is equal to some a3 k. Okay, but this of course implies, if I just look at this, that L2, L3 psi xk x naught is equal to 0, right? Because I'm just saying that this psi is now a common eigenfunction of both L2 and L3. So of course it's going to be killed by the commutator of L2 and L3. And then by the same argument as here, which I'm still ignoring the formality of, so this means L2, L3 has infinite kernel for all so the commutator is 0. Okay. Let's try and to appreciate what happened here. What happens is the following statement. I start with a differential operator L1, with a formal differential operator L1 of the form as we always describe. And what this says is that if I consider all differential operators of the same form that commute with L1, they will also commute with each other. So this means from L1, I'm going to get a commutative, what is it going to be? Ring algebra? Algebra of differential operators, right? Commuting with L1. Of course, I know some elements of that which are boring. So the boring element is I can just choose L2 to be a power of L1. That, of course, is going to commute with L1. If L1 itself were a square of some L, then of course L square and L cube will also commute, right? So these are some boring elements of this algebra, which is why this condition that I want, that it's most interesting to deal with a situation where these orders of the two operators are co-prime should really be here, because then I'm not getting into this issue with powers of differential operators. But in any case, getting from L1, I can always consider the set of all differential operators that would commute with L1. They will commute with each other, so they give me a commutative structure on this differential operators. And you can ask, can you classify such things? And this is where we're eventually going, but not yet. So here is the next theorem. And this goes to Birchnell Chondy in 1922 or something. It says the following. If a commutator like this is 0, then there exists a polynomial Q of alpha and beta such that if I take this polynomial and plug in L1 and L2, I get 0. Okay? This is to say, if I have a pair of commuting differential operators of the kind above, then they must satisfy a polynomial equation. Okay? What I was just mumbling, of course, if L2 is an L1 squared, I know what the differential equation is going to be, right? It's going to be alpha is beta squared or something like that. Or alpha cube is going to be beta cube. This is not very exciting. More exciting are the polynomial equations, which are not of this form, right? And the statement is that this is a general story. What I'm not going to tell you is, of course, well, if I have L1 commuting with L2, and I also have L1 commuting with L3, L1 and L3 will also satisfy a polynomial equation. And L2 and L3 will also satisfy a polynomial equation. And you can ask how these polynomial equations relate. And I'm not going to go there because I don't need to, but you should think about this. So let me try to give a proof of this. So let L of E be the vector space of eigenfunctions. L psi is equal to E psi. Okay. Then, of course, L2 preserves this vector space, right? L2 maps L of E to itself. Thank you. So L1. Okay. So I choose my setup has always been the same. I was somehow using L1 as the first operator I choose. I'm taking its eigenfunctions and I see how L2, L3, whatever acts on them. So that's the same setup. So I consider the L1 eigenfunctions with eigenvalue E. Since L2 commutes with L1, it will map such an eigenfunction to itself. This is a finite dimensional space. Okay. What kind of functions? Great. So the functions I mean, as always, as formal solutions, right? It's some space of formal solutions. I have, so far nobody has asked me again whether my coefficients U are smooth, holomorphic, meromorphic, so I will continue to ignore that. But the space psi, or the space L, is a space of all formal solutions.
In fact, I asked this, but
Well,
indeed this is not important.
this is not important. So whatever category you choose, you work in this category, this will still work. That's unimportant, yes. Did I suitably not answer your question? Or should I do better? Okay. Sure. Yes. Okay. So, I mean, this is n-dimensional in my setup, yes. So this is a map of a finite dimensional vector space to a vector. I mean, it's a linear map. So it has a characteristic polynomial, Q of alpha, comma, E, X. Sorry. Let me write it this way. QE of X. X, I cannot use X because X is my variable and it has nothing to do with this. B is a characteristic polynomial of this operator. It's a finite dimensional operator. It has a characteristic polynomial of size n. So I can just take that. Claim this polynomial as a polynomial is going to depend polynomially on E. Okay? So a priori here, for each E, I have a separate characteristic polynomial. So it's a polynomial in alpha with coefficients being some functions of E. But I claim that these coefficients of this polynomial themselves are polynomials of E. You can sort of convince yourself that there is some symmetry here. I start with L1, I can choose L2, right? And that will ensure that I can view this polynomial the other way around. Okay? Because what are the roots of this polynomial? The roots of this polynomial are the eigenvalues of L2 on the space LE. But I could run the same procedure backwards. I could first choose the eigenspaces for alpha of L2, and then L1 will act on each of such eigenspaces. I can take that characteristic polynomial. But that will depend polynomially on alpha and on E and somehow on alpha. But that's the same polynomial because this polynomial still tells you when you have a common eigenfunction. That's one way to see that. The other way is you can just write down what this really means. Because this is all completely explicit. I can just start solving term by term and I'll see what the coefficients of Q will depend polynomially, the formulas would be ugly, on E. So you can do that. So this means I can think of Q as just a polynomial in two variables, alpha, beta. Okay? But then again, as usual, if I take Q, L1, L2, this is 0 for any E, right? But this is a finite polynomial. It's a finite order differential operator, which is 0 for all eigenspaces. So this means it has finite kernel. So this has infinite dimensional kernel, so it means it must be identical to 0. Okay?
So may I suggest an exercise?
Please, thank you. For me or for the audience?
Explaining maybe simpler and purely algebraic.
Mm-hmm.
So consists of several steps. So first of all, show that if L2 commutes with L1, then it has constant leading coefficient. So L1 is given by the formula above with leading coefficient 1. Then if L2 commutes with L1, then it has constant leading coefficient. That's easy exercise. And then the second is consider the space of differential operators that commute with L1 of order less than or equal to n. This has dimension at most n plus 1. So this follows from 1 easily. And then you can use the rows of polynomial reading two variables to show that there is a polynomial equation in L1 and L2. This proof has the benefit that you don't have to consider eigenfunctions, and also it allows you to prove a stronger statement that in fact the ring of polynomials operators commuting with L1 is finitely generated.
This, of course, is completely correct and more conceptual.
So this is part 3, and then 4 show that the centralized L1 is finitely generated.
So this, of course, tells you more, but there is a reason I'm trying to do explicit computations. And eventually, we're trying to do Cauchy-Vier's proof of characterization of Jacobians by flexes. And somehow, there are explicit computations there. And just compute things, right? And much as I'd love to tell you a more conceptual proof of that, I won't be able to. There is a more conceptual, in some sense, algebraic geometric proof, but we won't be able to develop the machinery for that. So I'll try to tell you eventually Cauchy-Vier's original proof, which is somehow elementary again with many ideas. Okay, questions? So you want to compute the dimension of L2, which commute with L1. And then of order, I mean, L2 will start like that and will go to lower orders, right?
Well, yeah.
Yeah. Which
I need to make coefficient in front of T or DM, but it's constant.
it's a constant, it doesn't matter. Okay. So this. So let me read what Pasha says. So you first check that if you have L1, which is given by the coefficient 1 in order n, then any L2 that commutes with it must have leads in order term a constant times the m's derivative, no function here, right? This is something I was very sloppy about purposefully, because I was writing L1, I can always change variables so that it starts with a constant term. If I have L1 and L2, I can do this to L1. Why would I know that I can do this to L2 simultaneously, right? This was something that I was hoping to sweep under the rug, which I didn't succeed. Then once you do that, you can check the dimensional space of L2, which commute with L1, is at most m or m plus 1, depending on what you do with the coefficient here. Okay? M plus 1, including this coefficient, right? So if I set this to be 1, it's m. And that's just, you see that you can eliminate many terms by equation. Then you'll try to see how the polynomial ring in two variables grows, and then you'll convince yourself that you have a polynomial relation between L1 and L2 for all this m-dimensional space. All of them will satisfy a polynomial equation, which will allow you to answer my mumbling about, if I have L1 and L2, they satisfy some equation. If L1 and commutes with L2, they satisfy a polynomial equation. If L1 and L3 commute, then they satisfy another polynomial equation. You can ask whether that's the same polynomial equation. And this will go towards answering this question, but I was hoping to keep this for the future. Okay? Any questions so far? Yes. Why do I want n's powers here? Well, I want to have higher order differential operators, right? Because somehow I was saying if I had a first order differential operator, if you believe what I said, it's just differentiation with no coefficients, because I can scale out the top coefficient. So I certainly want differential equations support at least 2. The reason my normalization, if you wish, is such that the eigenvalue is k to the n and not e, because I'm somehow modeling myself on the exponential. So that's, if I differentiate the exponential n times, e to the kx n times, I get k to the n. And my solutions are deformations in some sense of the exponential. Okay? Other questions? Okay, so I have a question. How many of you have known all this before? Well, Pasha, yes. Okay. Raise your hand if this was too slow. Raise your hand if this was too fast. I can close my eyes and somebody else will count. Okay. There will be exercises. Okay. And notice this was purely formal, right? All I did was commute finite order differential operators, write solutions as some kind of series, right? And ignore questions in what formality this happens. There is no geometry so far. The only geometry you're going to see here is you get this polynomial q, right? It's a polynomial in two variables. So the polynomial q of alpha beta being 0 gives me a curve in C2. This is an algebraic curve which can be arbitrarily singular in principle. I never said anything about its singularities, and it will be, in fact, generically it will be singular. Of course, being an algebraic geometer, which I am, I don't like curves in C2. I'd like to further compactify them to P2 or P1 cross P1, which I can do. The singularities I will mostly ignore for these talks, even though they are a major issue that one needs to deal with many things. But this is the first time that you see that from some purely formal construction, you are suddenly getting an algebraic equation. You're getting a polynomial. Okay? I want to be, Pasha, I want to build suspense. I mean, there is a reason for that. Sorry, yes, but I'm trying to somehow push a different viewpoint. I mean, yes, but I don't want to think about that yet. So the message I want to say, this was a purely formal construction with differential operators, okay? And now I want to switch to the other side of the story, to curves. Eventually, these two stories will come together, but for the time being, view them as completely disjoint, okay? Too complicated. Yes, I should, but I'm not pushing this any further for now, okay? I want to take a step back, and for the next couple hours, I will not write differential operators on the blackboard. That's not the plan, okay? So now I want to tell you about curves and their jacobians. Yeah, if you want to learn the material properly, Don't learn it from me. Read the surveys, do things correctly. So there are some omissions here. There are some things that can be done differently. Everything can be done differently, maybe better. But I'm trying to push towards some particular viewpoint that will eventually lead us to tri-sequence flexes and all that stuff. And I'm trying to minimize things we see because we'll run out of time as it is at some point. So curves. So C is going to be a complex, compact, genus G, algebraic curve. Okay? And I'd like to define for you the Jacobian of the curve C. Okay? How many of you know a definition of the Jacobian of a curve? Raise your hand. How many of you know two different definitions of a Jacobian, which of course are equivalent? Okay. So I want to do this in different ways. So first, I want to say that if you look at the fundamental group of C, it has generators. I mean, you can choose generators, which I'll write A1, AG, B1, BG, such that pi 1 of C is generated by these things subject to just one relation. It's the product for I goes from 1 to G of the commutators AI, BI is 1. Okay? I expect that almost all of you, if not all of you, have seen this. This is an exercise for you, which is not an exercise for the exercise sessions, is to convince yourself of this. So if that's the case, and of course if I take the homology of the curve C with integral coefficient, this is just the fundamental group quotient by the commutator of the fundamental group. And this is just Z to the 2G, which is generated by A1, AG, B1, BG. I'm being sloppy. For me, these are both curves, actual curves, generators of a fundamental group. They're also generators of homology. I'll be purposefully sloppy with that. I have a symplectic pairing on H1, which I can define by saying that AI doesn't pair with AJ, BIs don't pair. Oops. But if I pair AI and BJ, then this is delta IJ. And I want it to be symplectic, so anti-symmetric. And an exercise is to think about in all possible ways to understand this. So think about this via Poincare duality. Think about it via Hodge theory. And in any other way you can think about this. Okay? So here is a definition. This is an analytic Jacobian. This is to say the Jacobian of a curve C, you take a vector space of holomorphic one forms on C, and you quotient by the dual of the integral homology lattice. Okay? what does this really mean? This means explicitly the following. So this is an equivalent description of this. So this is an explicit description. So given A1, AG, B1, BG, there exists a unique basis omega 1, omega g of the space of holomorphic one forms on C, such that the integral of omega I over aj is equal to delta ij. Okay? So I have chosen a basis for cycles, so the a's don't intersect, and I claim that there exists a unique basis of holomorphic one forms, this g-dimensional complex vector space, such that the integrals are just 1. Okay. Then the period matrix tau of C is the following matrix, is a matrix given by the integrals of these one forms over the B cycles, which are just some complex numbers. Riemann's bilinear relations are the following statement. It says that if I take this matrix, this is a G by G complex matrix, and I take its transpose, I get itself. So this is to say it's a symmetric matrix. And it also says that if I take the imaginary part of tau, so this is a matrix, a G by G real matrix, symmetric. And the statement is that this is positive definite. Okay? If you have never seen this, try to learn about this. This is not an exercise that you can do on the spot if you've never seen this. Okay? So that's a matrix notation, maybe, which I may or may not use, but we'll see. So Hg is a so-called Siegel upper half space. So this is a subset of matrices of size G by G with complex coefficients satisfying these conditions. If I think about it this way, what's the Jacobian of C? Well, the Jacobian is the space of holomorphic one forms, which is C to the G, spanned by all the omega, quotient by what? The integrals of forms over a basis of cycles, which is going to be Z to the G. This is the integrals over the A cycles, which are just normalized to be the basis vectors, plus tau Z to the G. Okay? In this subject, it's very common to always get confused whether you multiply on the left or the right, and I will continue this wonderful convention of writing it randomly and saying, if you want to do it correctly, be careful. Okay? But basically, what is this? This is a quotient of a G-dimensional complex vector space by a rank 2G integral lattice. Riemann's bilinear relation tells you that if you take this lattice and you tensor it with R over Z, you're going to get everything. This is to say this non-degenerate lattice. Okay? moduli space of curves, MG, this is the moduli space of genus G curves. AG is the moduli space of such things, of these things, for tau in the Ziegler-Lapa half space. When I say moduli, here, this means these are isomorphism classes up to biholomorphism. It means the same here. Okay? There is something I'm being sloppy about. There is a thing called polarization here, which we'll see in a second. But the point is that somehow the way I define, of course, I have a map from the Ziegler-Lapa half space to the moduli space of abelian varieties. And you can figure out what this map is. And this is actually a quotient by the symplectic group. Let me try to explain in a second what this means. So what's this map? So suppose I have some quotient of this sort, which is isomorphic to some other quotient of this sort. And I'm being very sloppy because I'm concealing the principal polarization, which we'll see more clearly next time. Then I claim that any isomorphism is actually a linear map, which leads to a linear map of CG to itself, which must map one lattice to another. So this should mean that I can get from one lattice to another by a linear transformation with integral coefficients. So this would look to be SL to GZ. The principal polarization will tell me this has to be a symplectic matrix. I don't want to go in this direction, but we'll do something like that next time. So let me say a little bit here, though. So definition, a complex torus is a quotient C to the G by some lattice where this is Z to the 2G embedded in C to the G, and that's a non-degenerate lattice, which is what I was saying. If you tensor over Z with R, you're going to get everything. So a complex torus is what you think a complex torus should be. It's a quotient of the complex vector space by a lattice. Okay? And a complex torus is called an abelian variety. A complex torus, let's not have notation for it, is an abelian variety if it is a projective variety. If there exists an embedding of it into some CPM. Okay? In which case, I'm going to think of this as an abelian variety inside CPN, which somehow is isomorphic to a torus, but it's an abelian variety in CPN. What is so nice about CPN? This has a Fubini-Studio metric. So if you're a differential geometer, you like the Fubini-Studio metric. If you're an algebraic geometer, you have the bundle of 1. Okay? And you can take this metric, you can restrict it to A. You can take this bundle, restrict it to A. So this gives a positive, if you're using the differential geometry language, ample, if you're using the algebraic geometry language, line bundle on A, which we'll call L. So definition, a complex, principally polarized abelian variety is a complex A is a projective variety A. I don't have to impose it because I'm going to say with an ample line bundle L such that the dimension of the space of sections of L is 1, and there is a group structure I can add points on A. Okay? So this is an explicit way to see this. This is a slightly less explicit way, and of course your exercises, this are equivalent. You need to unravel a little bit what is equivalent. So this is not quite correct. I shouldn't take an ample line bundle. I should really take its Chern class, because an abelian variety I can translate. It's a torus. I can add a point of it to itself. This will translate the line bundle to a slightly different line bundle. I don't want that. So I really want the C1 of an ample line bundle here. And in this picture that I was advocating above, you need to understand what it really means for principal polarization. So principal polarization is this condition, that I only have one section of the bundle and not many more, right? So that's the definition of an abelian variety. And in the remaining -1 minute I have, I want to say how this relates to our setup. And the setup is there is a theorem. This is a Tarelli theorem. Is if I take a curve C and I send it to its Jacobian, which is a principally polarized abelian variety, this is an embedding. Okay? Okay. This is a nice theorem, except it's false. So it is true, but not really true. So this is an embedding, or the next sentence you can ignore. This is an embedding of course moduli spaces. This is a 2-to-1 map of stacks. And it is essential for much of what I'm going to say eventually, but I will conceal this, okay? So what does this say? This says, if I have a curve, I can construct from it its Jacobian by this construction. And you get a principally polarized abelian variety. The statement is, if I give you a principally polarized abelian variety, and I promise to you that this is a Jacobian, it's a Jacobian of a unique curve. That is what this really says. Okay? That's what I just said is a true statement. Okay?
It also did you mean to say that AG is not a label?
This is correct as written here. I was very sloppy when I said isomorphism classes. So there should be isomorphism classes preserving principal polarization, which I didn't carefully write here. Okay? So that's an explicit picture. This is not how I want to think of it next time. So next time I'll start by telling you a different viewpoint on Jacobians, more geometric, and I want to talk about Riemann theta singularity theorem and eventually get to the statement about the existence of trisecants. This will probably take us all of tomorrow, essentially. Yes, so here I'm being rather sloppy about where the principal polarization is. So the principal polarization is that pairing, and the matrix is diagonal and with all ones, which is to say it's principal polarization, otherwise I'll have some integers along the whatever anti-diagonals. So here I should say preserving principal polarization. And by principal polarization, I should really mean the first Chern class of an ample line bundle, so or an ample line bundle up to translations, which is equivalent. Okay, I think that's it. Before I say that's it, how many of you have known all this story about Jacobians? Because I need to adjust pace. Okay. How many of you thought this was too fast, the Jacobian part? Don't be shy. Okay. How many of you thought this was too slow? Well, I'm sure there are some people in the audience, maybe slightly older people in the audience who feel slightly less young people feel that. Okay, that's it for today. Thank you.
Let me see. Let me see if there are any questions, including questions online. You can ask questions in the Zoom chat.
So the Jacobian is principally polarized because of this. So the polarization of the Jacobian is given by this intersection on A and B cycles, right? So the A and B cycles, you can just draw them. So if I have a curve of genus 2, this nice curve of genus 2, and if I find some colored chalk, which is here, I can draw for you A and B cycles explicitly, which is really a proof that this is always can be done if you make this a bit more formal. So I can choose this to be my A cycles. This is A1, A2, B2, B1, right? So I have just demonstrated for you cycles that have these intersections as I claim they do. And then if I look at the matrix of their intersections, so I write A1, A2, B1, B2, A1, A2, B1, B2, the matrix has zeros here, and has identity matrix here. I'm being sloppy about my sign, so maybe the opposite, doesn't matter. But these are ones here, right? Which is to say it's principal polarization. So in principle, I could have a matrix which would look like that. In integral homology, these are a basis of integral homology. They're not just a basis of complex homology, it's a basis of integral homology. If I were unlucky, I didn't choose a base, I may have some multiples. And this would not be a principal polarization. This would be a polarization of type D1, D2, where this is some integers. So the principal polarization is because I can do this for any Riemann surface. How can you update? So the question is, from this picture, how do I see an ample line bundle L? So an ample line bundle L, I don't want to see. I want to see its first Chern class. So the first Chern class is C1 of L, right? This is a class in second homology, cohomology maybe, of the Jacobian of C, right? Which is really not just in second homology, but is in H11, if I look at this carefully. But this is an H11, so this is more or less a pairing on first homology. That's your pairing on first homology. And you would like to transfer from this to that. Tomorrow I'll tell you a completely different picture of Jacobians, which has, the period matrix will not show up.
Okay, may I interject here? I think Sam made an excellent point that there are exercises and that the exercises should be done. But I also think that it's nice to do exercises together. So we do have exercise sessions and discussion sessions for each of the courses. Okay? Note the structure. There are two rooms, this room and a similar room in the library building A7 that is downstairs by the steps. And we don't want to formally split you that let us from A to M attend the first course exercise session in the first hour and the second exercise session in a different room in the second hour, but try to balance, okay? Make sure that half of the people spend 1 hour here and 1 hour in the other room and the other way around. So we will have TAs who know how to solve all these exercises and will help you, and also have the instructors who might know how to solve all these exercises and would also help you. So take advantage of this. Okay? And I suggest we take a coffee break. And questions like this are best discussed slowly during this discussion exercise session.
Хотелось бы знать, какая.
All right, so it's my pleasure to introduce the second speaker, Pavel Etingov from MIT. He will give a talk about, he will give 5 talks, 5 lectures about Hitchin systems and their quantization. Okay, Pavel.
Can you hear me? Yes. Okay. It's my pleasure to give lectures here in BIMSA, and especially that give lectures at the school dedicated to the memory of Igor Krichever, who was one of my teachers and influenced me mathematically in a major way. There is a nice article in the Notices of American Mathematical Society written in Igor's memory by people who knew him well, including several people in this room. And I highly recommend reading this article. You'll learn a lot about his life if you have not met him. And now let me start my talk. I'm Pavel Etingov. Good morning, доброе утро, ни хао. So I will talk about things like Hitchin systems, classical and quantum, and it's about Langland's correspondence. And all of these things correspond to doing analysis, geometry, and arithmetic on, well, Langland's correspondence in the case of function fields, mostly. And all of this corresponds to doing analysis, geometry, and arithmetic on a geometric object called band G of X. So this is the moduli space, and technically it's a stack of principal G bundles on a curve X. So X will be a irreducible smooth projective curve over some field. G is a reductive algebraic group, and to this data one assigns a certain very complicated geometric object, this moduli stack of principal bundles. It's very rich, and when we do geometry analysis or arithmetic on this object, we see all these things. In particular, Hitchin integrable system will be one of the major topics, and this is a large class of finite dimensional integrable systems attached to this data, which entails many, maybe even most, of the interesting finite dimensional integrable systems that are known. They are special cases of this system. And this system also played a major role in the work of Igor's. So I will talk about this already starting today. So let me not talk much about the motivation, because it is better if I start with some basic definitions, and then we talk about the content later when we are more prepared. So the first basic So today will be, much of today will be a review of some basic algebraic geometry related to this object. And as I said, it is complicated, so I will sweep under the rug a lot of things. Maybe some of them will be discussed in the exercises. So the first thing I want to talk about is, so what is a principal G bundle? So let's say X is an algebraic variety over a field K. A lot of the time it will be a curve, which means one-dimensional and smooth and also projective, irreducible. For the field K, you can keep in mind complex numbers, but actually it will be also important to consider non-algebraically closed fields such as finite fields or p-adic fields. And G is going to be a reductive algebraic group. And I'm going to assume that it is connected and also split. So in this case, it's defined over any field you want, basically over the integers. It's attached to a root datum. And basic examples to keep in mind is a general linear group GLN, or special linear group SLN, or projective general linear group PGLN, which is quotient of GLN by the scalars. There are also classical groups such as symplectic groups, orthogonal groups, and in particular important case, n equals 1, GL1 is just the multiplicative group, and you can also consider tori, which are products of several copies of the multiplicative group. So first, I'm going to define the notion of a principal bundle. For this purpose, I don't need to assume that this algebraic group is reductive, connected, or split. So first, let G be any affine algebraic group over K. So what is a principal G bundle on X? So definition, a principal G bundle, or sometimes also called a G torsor on X, is a variety P with a map to X. So people say variety over X. Algebraic geometry call it variety over X, which means variety equipped with a map to X, with a right action of G, preserving pi, which is locally, and locally technically mean étale locally, on X is isomorphic to action of G on the trivial bundle G cross X to X, by right multiplication. On the G component. So what does it mean? So that we have an so there exists an étal open cover UI of X with P restricting to UI isomorphic to G cross UI in a G invariant way and commuting with pi. And this is just the second projection. What? Yeah, globally trivial means that there is just, you can use just one chart UI, which is X. So that's a special case. And now, well, there is this word étal here, which is not going to be very important, but I still should say what it means. So open charts, of course, in geometry are just open subsets of X, but étal chart is a little bit more general. So what is an étal chart? So this is a open set U bar inside X. So by open, I mean, of course, Zariski open, because we are in algebraic geometry, and unramified cover, algebraic unramified cover from U to U bar. So this means that étal chart means that I'm covering some open subset of X, rather than just taking the subset itself. So it's slightly more general. But you can do the same, everything with such étal charts. For example, you can take the intersection, which by definition is the fiber product. So I'm going not to talk about this too much, because actually it's not going to be very important. And in particular, this P UI is by definition just the product of P with UI over X, which means it's pairs of points that map to the same point of X. So in other words, UI are not really open subsets of X, but they're slightly more general. They're finite unramified covers of open subsets of X. So what this means is that, but again, for me, it's not going to be very important that I have to take these covers. And that's why when I talk about these things, you can think of UI just naively as open subsets of X in the risky topology. So a principal bundle can be constructed can be realized by so-called clutching functions. And so these are functions Gij from the intersection Ui with Uj into G. So these are regular functions. And as I said, this is just by definition the product over X. But again, you can think naively of this as just open subsets and intersections. And of course, when the intersection is non-empty, and this should satisfy some conditions. Well, first of all, Gij. So this is a clutching function, which is a transition map from Uj to Ui. So Gij composed with Gji is the identity. And also Gij composed with Gjk composed with Gki is the identity. And so this is called the one cocycle condition. So it's a condition for check one cocycles. And this should be satisfied on the triple intersection, Ui, Uj, Uk, whenever it is non-empty. And this is, of course, so the idea is that we are gluing trivial bundles on UIs, like here, by using these clutching functions. And in particular, if we change this Gij on the left by some Hi, and on the right by some Hj, then it will not change. The bundle will be isomorphic. So this means modulo the following transformations. So maybe I should say principal G bundles are classified by so modulo the following transformations. Gij goes to Hi composed with Gij composed with Hj, where Hi are some regular maps from Ui to G. So this means that this Gij, so this is a one cocycle condition, so this means that this Gij is a one cocycle of X with coefficients in the sheaf O Xg. So this is sheaf of G-valued regular functions. On X, well, sheaf of G-valued regular functions. And this means that cohomologous cocycles define the same bundle, define isomorphic bundles. Oh, yes, thank you very much. Yes, J inverse. Well, I mean, it doesn't, yeah, that's right. So, so it's Hi, Gij, Xj, Hj inverse. So, and so this means that these G bundles are classified by the set of equivalence classes, which by definition is the sheaf cohomology H1 of X with coefficients in this sheaf or Xg. And this is étale cohomology because we are using étale covers. So there are some standard notions. So what is an associated bundle? So if you have a group homomorphism phi from G to H, then any G bundle on X gives rise to an associated H bundle, because we can consider these transition functions which lie in G as being in H by applying this phi to them. And in particular, so if G equals to GLN, then so actually, so then a principal G bundle is, well, the same as a vector bundle of rank n. So because these transition maps can be used to glue bundles of the form G cross UI, GLN cross UI, where here you have a matrix, or you can put a vector here and use the same way to glue. And actually, by saying that this is the same means that there is a bijection, moreover, an equivalence of categories. So it is equivalent to consider vector bundles or principal GLN bundles. And also, if you have a row from G to GLV, an algebraic representation, then, well, GLN, algebraic representation, then every G bundle B on X, maybe I should call it E on X, gives rise to associated bundle associated vector bundle E sub rho of rank n. Sorry, rank small n. So these are some trivial generality. And of course, this definition is completely parallel to the one that is used in differential geometry. So analogous to the definition in geometry or topology, in which case we consider, instead of regular functions, we consider C infinity functions. So if you want to consider topological bundles on manifolds, you consider continuous functions or smooth functions. If you want to consider flat bundles, then you consider locally constant functions. But otherwise, the definition is completely the same. And of course, in classical topology, you do not need to consider these étale open sets. So I will explain why they are necessary in algebraic geometry in a moment. But as I said, for what we will do most of the time, this is not going to matter. And similarly, in analytic geometry, complex geometry, so we have the same story with holomorphic functions. So in topology, G is going to be a topological group, X is going to be a topological space, or X is a manifold, G is a Lie group, and we have smooth functions. And in analytic geometry, X is a complex manifold, and G is a complex Lie group, and we use holomorphic functions. In all these settings, we use just ordinary open subsets. And so then we have, we can obtain a principal bundle by gluing. So if we are given such a cocycle, we can obtain this principal bundle by gluing. So let me, in algebraic geometry with étale covers, this is a little, so if you have a usual open cover, you literally glue, if you have a point in chart ui and point in chart uj, which correspond to the same point on x, then you just glue fibers at those points by using the corresponding map gij. If you have étale covers, it is slightly more complicated. You use something that is called faithfully flat descent, which is a similar procedure with coverings of open sets. I'm going to skip it. But in any case, if you take pi inverse of x, where x is a point in x, this is called the fiber of G at x. It's denoted P sub x. And this is a principal homogeneous space for G. Which means that G acts simply transitively on this Px. Well, this is a story of an algebraically closed field. If you do not have algebraically closed field, then you should consider points not just over the original field, which actually may be none, but also over some field extensions. And also, I should mention here Serre's Gaga theorem. And so this is analytic geometry, algebraic geometry in French. And the theorem says that that actually it doesn't matter. So if X is a complex, if X is a complex projective variety, then analytic G bundles on X is the same thing as algebraic G bundles on X. Well, again, the same thing means that here you have an equivalence of categories, so everything is the same. There is a one-to-one correspondence between all the structures, and correspondence is in this direction obtained by analytification, which means that you every algebraic variety over complex numbers smooth. So let's say smooth can be viewed as a complex manifold, and any G bundle can be obtained. So for any algebraic G bundle, you can view it as an analytic G bundle. And so this is an equivalence. This is a kind of far-reaching generalization of the fact from complex analysis that a meromorphic function on, let's say, projective line, for example, is rational. Now, I should mention that why do we have to consider étale in general? Well, because in topology, we do not have to do this because we have neighborhoods of points which are contractible. which have trivial cohomology. And that's why we can use these neighborhoods to test and to compute global cohomology. In the risky topology, let's say on curves or on line, the risky open sets are just complements of finite sets. So you have the complex line and you remove finitely many points. This, of course, does not, there is no way to make such sets contractible. And because of this, you have some difficulties. So for example, you can consider the following principal bundle. So you take P, which is just punctured complex plane, and it goes to C star by the map Z goes to Z squared. So this is a principal mu2 bundle, which is really Z mod 2, multiplicative group of roots of unity of order 2. So it's a group consisting of 1 and minus 1. And it doesn't trivialize on any non-empty Zariski open set in C star. Well, because what happens, what is this bundle? It's a bundle such that if you go around the circle, so you have this punctured complex plane, and if you go around the circle, so you have a monodromy, which is multiplication by minus 1. If you remove finitely many points, that's not going to go away. So in order to think about bundles this way, we need for every bundle to have an atlas of charts on which, on each chart, the bundle becomes trivial. And so this doesn't happen here. And that's why we need to take finite coverings to trivialize this monodromy. Well, if G is connected, this example is not a problem anymore because it happened because the group was disconnected. But actually, this may still happen. Say for surfaces. But this is much more subtle. So there is an example which you can find online, but I'm not going to talk about it. There is a theorem it's a non-trivial theorem of Borel and Springer. And says that so it can fail when G is connected reductive for surfaces. This is the case that we're interested in, connected reductive. But Borel and Springer showed that if X is a curve, a smooth curve, then any principal G bundle on X is Zariski locally trivial. And this is for connected reductive groups. I should say that for some connected reductive groups, such as GLN and SLN, this is always true. So it is not for GLN, for example, there is the theorem which is called Hilbert's theorem 90, which says that this is true for any X. But for other groups, for example, PGLN or orthogonal groups, symplectic groups, for orthogonal groups, symplectic are fine, but orthogonal groups, this can happen. And but in any case, for curves, this doesn't happen. And so this means that we can forget about this et al. Story, which is only necessary to make a correct definition in general, and think about ordinary Zariski open covers. So any G bundle on X, which is a curve, will trivialize if you remove a finite number of points. And in fact, if G is semi-simple, it's also a non-trivial theorem of Harder. And later it was generalized to families by Drinfeld and Simpson, which says that if G is semi-simple, then a G bundle on X, smooth projective curve, so on any G bundle on any on a smooth affine curve is trivial. So this means that it is trivialized if you remove just one point. So this is, I should say that this is false for non-semi-simple groups, such as GL1. So in the case of GL1, so let me do an example. So in the case of GL1, the set of isomorphism classes of bundles on X, which is the same as line bundles in this case. Well, I said that it was the same for GLN as vector bundles of degree n, of rank n. And so in particular for n equals 1, it is just line bundles. And this is true for any x. So this is the Picard of x. And for curves, I suppose as Sam will explain, maybe next time, I don't know. Picard has the following structure. So a line bundle on a projective curve, smooth reducible projective curve, has a degree. It can be bundles of every degree. And they form also a group. So this is a group by tensor product. Tensor product at the level of these transition functions is just multiplication of them. And so this group is included in an exact sequence. So there is a degree map to the integers. And the kernel is peak 0, which is degree 0 bundles. And this is exactly the Jacobian of X. It's another definition of Jacobian that will be probably tomorrow in Sam's talk, right? So this Jacobian is a complex torus of dimension G, where G is the genus of X. And so here, what happens is that every point so if you remove a point, so if you compute Picard of X without a point, well, it turns out that this is just, then the notion of degree no longer makes sense. Because this means that you can consider bundles. So this is basically pick x modular the subgroup generated by O of x, which is a line bundle whose sections are functions with a pole at x of order at most 1. And so this is just, this sequence is split. There is a splitting. It's not canonical, but it exists. So this is just a product of these two groups. And this is a quotient by the z, so this is just Jacobian of x. And so, so this means that if your genus of x is bigger than 0, this means that bundles are not trivialized. So cannot be trivialized in general by removing a point. So every bundle can be trivialized by removing some finitely many points, but you do not know which ones in advance. If I give you any sequence, any finite collection of points, and you remove them, there exists a bundle which does not get trivialized when you remove those points. Okay, so now I want to talk about moduli. So this was a kind of first topic, just basics. And then the second is moduli, space of bundles. On smooth projective curves. So we have, so for every x and g, and for me x is going to be a smooth projective irreducible curve, and g is going to be a connected reductive group. We have the set Ban g of x of k, and this is the isomorphism classes of principal G bundles on X defined over K. And this is just a set, but actually we have a lot more than that. We can do this not just for K, but we can do it for any field extension of K, or more general ring extension of K. So more generally, since we're doing algebraic geometry, there is no problem to take extension of scalars and consider bundles defined over some extension of K, which means that all these Gij will have coefficients in this extension. If A is a commutative K algebra, then have the set of equivalence classes Ban G of X of A. So this means that we have a functor of points, which is maybe denoted Ban G of X, which sends A to this set Ban G of X of A. So this is the kind of functor that we consider in algebraic geometry when we define schemes or affine schemes. And so it's actually even more generally, you can consider so when we consider schemes, we also have such you can define a scheme by as a functor like that, which satisfies certain properties, which is called representability by a scheme. But this is not satisfied for this thing. So this is not representable by a scheme. And the reason is that bundles. So the different. So rather, it is an algebraic stack. I'm not going to get into the details. So to set up the theory of algebraic stacks would take a separate course, which I'm not qualified to teach. So, basically the reason is that bundles can have automorphisms. So schemes, the main difference between schemes and stacks is that scheme consists of just points, which are just points and nothing else. But stack, every point has a group of automorphisms. So it's a category, actually, where every point has a group of automorphism. And remembering this group is important. In particular, it affects what kind of functor you get. So an example is the following. So let's say G is a finite group. Well, you can consider principal G bundles on a point. So you, not principal G bundles on a point, but you can consider a point, let me call it star. So you have this stack star modulo G, which is denoted by BG. And so this is called the classifying stack. And it's defined, so if you want to take points, so functor of points like mappings from some affine scheme, let's say spec A into star mod G, would be just the category of principal G bundles on X, on S. By the way, I defined bundles on varieties just for you to feel more comfortable, but actually the better generality is to talk about bundles on schemes. The difference there would be no difference whatsoever. Just replace the word variety by the more general word scheme. So that's a kind of thing. So this is a stack where there is just one point, but this point has an homomorphism group G. And so if you take a particular point in this bund G of X, which corresponds to a particular bundle, that point is not an ordinary point, but it is an object like this. And so in fact, so more generally, you can consider the following stacks, which are called global quotients. So stacks are, algebraic stacks are a kind of globalization of the notion of quotient of a variety by group action. So if Y is a variety and G is algebraic group, maybe let me call it H to distinguish it from G that I considered before, acting on Y, then to this you can attach the stack Y mod H, and the action is going to be a right action. As in the definition of principal bundles. Functor of points for this stack would be that mappings from S to Y mod H would be the same thing as an principal H bundle P to Y with a morphism principal bundle over S with the following map. So S maps to Y. So with a map that commutes with H action. So a map from S to Y over X, H by definition is a principal H bundle P over S together with a mapping from this total space P into Y, which commutes with the H action. So in other words, the goal of this is the following, that if your group doesn't act, so if your group H acts freely on Y, then the quotient is just usual quotient, at least when this group is, let's say, GLN. But in general, if you have stabilizers, quotient has bad properties as a topological space. And the idea of the theory of stacks is just not to take the quotient. Think about this quotient as Y with an H action and never take the quotient. And try to rewrite everything in terms of Y and H rather than the quotient. That's correct, yes. Yeah, so that's a question. So it is principal G bundles on S. So it's a question yeah, it depends. You can also do the same thing in topology. Well, in that case, what you normally do, so in that case, you can, because you consider things up to homotopy, what people do is instead of talking about stack, they can realize the stack by a topological space. And so for this purpose, you replace, so you have the path space. So every group G acts on some contractible space. And then instead of star, you put this contractible space. And then you actually get your space. But often it will turn out to be infinite dimensional, like even if you take a group Z mod 2, for example. But this is a different point of view where you do not define this space, but just work with this stack. Okay, so so what happens is that it's a fact that I will just state now and maybe elaborate on later. So this bun G of X can be defined. So it's not, bun G of X is not a global quotient like that. And it's also not of finite type. So it cannot be represented this way when Y is a variety or scheme of finite type. But it can be represented as a nested union bun Gx J, let's say, of open subsets which are of the form Y over H, where Y is a smooth variety and H is a nice group, let's say, GL and J for some J, for example. So in other words, it has charts. It is not globally of this form, but it has charts which are of this form. So if you always work on this stack locally, and if you work on it on some neighborhood of a point, you can always think about working with a quotient like that. Although there is no natural representation. There are different, like for example, if you have H is a subgroup of some group H prime, then you can multiply Y over H by H prime, and this will have an action of H prime. So Y over H will be equal to Y cross over H with H. Let me put it here. With H prime, modulo H prime. So there are different representations of the same stack in this way, and there is no particularly nice representation here. So that makes it very subtle to work with this thing. But in particular, you get a set for every field K. Let's say K is a complex number, so you do get a set, ban G of X of K, but it is not a very nice object other than being a set. It's a topological space, so ban Gx of K is a topological space. Well, because when you have a quotient, for example, of X by H, you do get of Y by H, you have a topological space, but with very non-separated topology. So points don't have to be closed. So closure of a point may contain other points. And in fact, in most cases, there will be, like for projective line, in some cases, like for example, when X is P1, you will see that there is just one point, the trivial bundle, whose closure is everything. So this is the difference with schemes, because schemes are also topological spaces, and they are not terribly separated. For example, they are not Hausdorff, but they are more separated than this, in the sense that points at least are closed. Well, here, well, the points over the field are closed. Here, that's not going to be the case. You will see this more concretely in examples. Okay, so yes. Bun G of X of A. Well, it is the same thing. It is bundles on X, G bundles on X defined over A, which means that you have some open cover and you have some GIJs, but these GIJs are defined over A. So, okay, this is a map of, let's say, on a curve, these all are affine. Map of affine variety is just a map of rings of functions. But instead of map of algebras over K, you consider map of algebras over A. So it tensor up everything with A over K. Huh? Yes. Okay, so let me do some examples. So for example, SLN bundles is the same thing as, so I said already that GLN bundles are vector bundles of rank n. SLN bundles are vector bundles of rank n with trivial determinant. So top exterior power, and PGLN bundles is the same thing as vector bundles of rank n up to tensoring with line bundles. All right, so let me now do something concrete. So first of all, for GL1 bundles, well, we have a bun G of X is peak X. which is really the product of pick 0 of x with z, non-canonically, but it is. And it is a stack because every bundle has a group of automorphisms. So for any line bundle L, automorphisms of L is just C times. Let's say we're working over complex numbers. So points do have automorphisms. But in this case, all points have the same group of automorphisms. So this means that this is a stack which is not very different from a scheme. We can rigidify the situation by, for example, considering bundles together with a point in one of the fibers. And then the C star will be killed by because we have to preserve that point. And then we will get a scheme. It's an infinite type scheme because there are infinitely many connected components. But otherwise, it's a very nice scheme. And every piece is just an abelian variance. But so this is not too different from a scheme. But of course, if you consider GL2 bundles, or even SL2 bundles, even if you do the simplest possible curve, which is P1, then the situation will be much more complicated. Because in this case, we can have automorphism groups of any dimension. So the more degenerate your bundle becomes, the bigger the automorphism group will be. So let us see this concretely. So let's consider, so it should be a bundle with trivial determinants. So first of all, what are GL1 bundles? So what are line bundles on P1, which is Picard group of P1. Well, this is just Z because Jacobian of P1 is 0. And so all bundles are O of n, where n is in Z. So it's a bundle of degree n. And so this is just O of 1 to the nth power and O of 1. So how to construct O of 1? Well, I mean, you have two charts on P1. So P1 is the union of affine line A1 with infinity. And so there are two charts, U0, which is just A1, and also U infinity, which is P1 minus 0. And so there is a, so we just need to one transition, and then every vector bundle on A1 is trivial. Well, this follows from the fact that vector bundles are the same thing as finite projective modules. And every finite projective module over the polynomial ring in one variable is free. That's actually true for polynomials in any number of variables, but it is much harder. It's a theorem of Quillen, which was conjectured by Serre. But in one variable, it's an elementary exercise in commutative algebra. And so this means that we can use these two charts. So we have these two charts on our, so if you have complex numbers, you have Riemann sphere. And there is two charts. One is sphere without the north pole, the other is sphere without the south pole. So the intersection is A1 minus 0, which is just the multiplicative group. So over complex numbers, it is just C star. And so we need to have a regular function, G, from U0 intersecting U infinity to Gm, which is the clutching map to pass from the infinity chart to the 0 chart. And so this is just Gm to Gm. So this is a function which is non-vanishing, and there are such functions are all of the form a constant times z to the n, where this is a non-zero constant. And this constant can, of course, be absorbed by rescaling. By rescaling, for example, on U0 or U infinity. So we got g of z equals to z to the n. And this gives the bundle O of n. So this is the realization of O of n. And so in particular sections, so in particular, so if you have a P to X is a G bundle, then sections are such maps which split the projection. So composition is the identity. And we can talk about section of principal bundles, section of vector bundles, sections of line bundles. So sections of O of n are pairs of numbers. Well, let me call it V0 and V infinity. So a section, sorry, not of numbers, of polynomials. Yeah, but they have to be, so, okay. The maps should be, so section would be a map from, say, U0 to Gm. So it's a non-vanishing polynomial, which means it has to be a constant. So sections are pairs of numbers. Let me call them V0 and V infinity. Sorry, no. They are pairs of, yeah, function, non-vanishing functions. Yeah, pairs, okay, V0, V infinity, such that or maybe I should call them F0 and F infinity, such that F0 equals to Z times F infinity. So what, okay, so they are sections. So yeah, sections are a line bundle. So this means they don't have non-vanishing condition, line bundle sections. And so this is polynomials. So this is polynomial of Z, and this is polynomial of Z inverse. And they should satisfy this condition. So, Z power n, yes, thank you very much. Right, and so you see that from this that, well, f0 is determined by f infinity, and f infinity has to be a polynomial of degree at most n, so it has n plus 1 dimensional space of sections. Okay, so now suppose you have so you can consider now GL2 bundles or SL2 bundle, O of n, let's say O of n plus O of minus n. So this means that the G is going to be z to the n, 0, 0, z to the minus n. And so, so what are automorphisms of E? Well, they are the set of matrices A11, A12, A21, A22. Well, A11 is a map from O of n to O of n, so this is just a scalar. So A11 is going to be a scalar. A22 is also a scalar. So if we are over complex numbers. Now, A21 is a map from O of n plus O of minus n. So let's assume that n is bigger than 0. Then home from O of n to O of minus n is, so from this, I derived the dimension of sections of O of n is equal to n plus 1 if n is at least 0, and 0 if n is less than 0. So this follows from this description here. Because if n is negative, there is no such pairs. And if n is positive or 0, there are n plus 1 dimensional space. And so this is the same. I can tensor this with O of minus n, and I get form from O to O of minus 2n, which is the same as sections of O of minus 2n. And so we see that this is just 0 if n is positive. And so, so that means that the A21 is going to be 0. And in a similar way, A12 is going to be a section of O of plus 2n. And this is a 2n plus 1 dimensional space. So this means that the group of automorphism of E consists of things like C1, C2, 0, and some alpha. And this is in the 2n plus 1 dimensional group. But of course, we want it to be an SL2, so this should be C1 and C1, C and C inverse. And so dimension of this group is 2n plus 1. Sorry, it is, no, it's 2n plus 2. And so this grows as n increases. And so this explains that we have this phenomenon, that this stack is going to be complicated. For SL2, it's not, for P1, it's not too complicated because we will see that the point, there are very few points in a second. But for X being genus greater than 1, this stack is very complicated. And that's why Langland's theory, Hitchin system theory, is very rich. So let me now classify rank 2 vector bundles on P1, and then rank n vector bundles on P1. Again, you can think about complex numbers and think in terms of geometry of holomorphic bundles. if you're more comfortable with analytic techniques. So the theorem we're going to prove that every every rank 2 vector bundle on P1 is isomorphic to O of M plus O of N for a unique pair M less or equal to N. Well, the uniqueness is clear. So uniqueness is the following. So from that calculation there, we see that N, we can recover N from E by, so N in fact is the maximum I such that home of O of I into E is not 0. Because if you map O of I into the sum, if I is bigger than both M and N, there will be no maps. Now the existence is more interesting. And for this purpose, to prove the existence, we are going to see that, in fact, so let's fix rank 2 vector bundle E on P1. Then it has a meromorphic section. Well, because it trivializes on some open set, for example, on U infinity or U0, and that has a section. So that would be a meromorphic section which has a pole at the missing point. And so this means that we have a map, non-zero map from O of M into E for some M. Well, so a section is a map from O to E, but the section is meromorphic. It has some poles. And so if you want to kill the poles, you have to take a negative M, accounting for those poles. And so we can also assume such that phi is non-vanishing. So it could happen if you have a map of bundles that the whole fiber at some point goes to 0. I don't want that to happen, but I can avoid that, because if that happens, then I can raise M by allowing multiplying by the corresponding point to make sure that that doesn't happen. And so this means that this is in fact an inclusion of vector bundles. So we have a short exact sequence O of M, E, O of N, 0. Well, we are not. So if M is bigger than N minus 1 or equal, then so such bundles are classified by X1, right? So this is classified by X1 from the bundle here to the bundle here. So this is the first cohomology with coefficients in the product of inverse of this with this. But then there is Serre duality, which says that this is H0, dual to H0, with coefficients in the bundle dual to this, tensored with the canonical bundle. Tensored with canonical bundle. But canonical bundle for P1 is O of -2. So this is going to be O of n minus m minus 2. And so if you have if m is bigger or equal than n minus 1, then this is negative. So x1 is 0, and we have a direct sum. So in this case, we have nothing to prove. And so we can assume that m is at most, that m is strictly less than n minus 1. And in this case, let R, well, in this case, it's not in general true that this is a direct sum of O of m plus O of n. It could be sum of O of m prime and O of n prime, such that, well, the degree of this bundle is m plus n, so that's fixed. But the numbers could be different. And so in order to find the correct numbers, let R be the maximal integer such that hom from O of R into E is not 0. So we know from here that that's the right number for the bigger number. And so, well, that exists. You cannot take R indefinitely big, because then, well, you map O of R into this extension. There is a long exact sequence with maps to this thing and map to this thing. But if R is bigger than both of them, then both of those will be 0. So the thing will be squeezed in between and will still be 0. So, so this exists. And then, so what is the, so how can we realize this bundle? Well, we have the clutching map, and here we have the subbundle. So this is z to the m, here is a z to the n, and here is a certain function f of z, which is a Laurent polynomial. And in fact, we can reduce so this is a Laurent polynomial. And then we know that we can multiply, can change G by H1 G times H2 inverse. And so H1 is 1, 0, 1, phi polynomial of Z. And H2 is 1, 0, 1 polynomial of Z to the minus 1. And so it is easy to check. It's a nice exercise, simple exercise, by applying these H1 and H2, we can reduce uniquely to the situation when F has monomials Z to the S, where S is strictly between M and N. So note that when M is bigger or equal than N minus 1, there is no such S, and so this means that this will be 0, which is exactly what we already see. And so now so what is a section? So a map O of R into E is a section of O of minus R times E. So with the transition map, is this thing multiplied by minus R. So this is going to be Z to the M minus R, Z to the N minus R, and Z to the minus R times F of Z. And so if you compute what a section means, pair, well, first of all, it is some polynomials x0 of z, y0 of z, and also some polynomials x infinity of z inverse and y infinity of z inverse, which satisfy some equations. And the equations are the following: z to the r, okay, so y0 of z equals to z to the n minus r times y infinity of z inverse, and x0 of z is z to the m minus r x infinity of z inverse plus z to the minus r f of z times y infinity of z inverse. And so for this to be possible, for having a non-zero such thing, so for having such thing, so such section, so I can actually put r on this side, z to the r of this equals to z to the n times this, and z to the r times this, z to the m times this plus this. So this means that this has no monomials below r. So that's actually this y0 and x0 can be forgotten about. I just need to find y infinity and x infinity in such a way that these expressions have no monomials below r. And so what does it mean? For this expression to have no monomials below r, this means that the degree of y infinity is at most n minus r. And then we can allow arbitrary polynomial with that property, and this can be used to cancel certain. X infinity can be chosen arbitrary polynomial. So this means that we can kill all terms above m, and so this means that the result is that the condition is that f of z times y infinity of z has no terms of degree between m plus 1 and r. Because all the terms below degree m can be removed by means of this, by choosing some x infinity. All right, so this is how many equations and how many unknowns. So we've got n minus r plus 1 unknowns, which are the coefficients of this polynomial here. And r minus m equations, linear equations, homogeneous linear equations. So solutions exist if the number of equations, non-zero solutions exist if the number of equations is bigger than the number of unknowns, which means that r minus m is bigger. What? Yes, the number of unknowns bigger than the number of equations, so less than n minus r plus 1, which is the same as less or equal than n minus r. So this is equivalent to saying that r is less or equal than m plus n over 2. Right? So in particular, this means, so the maximal r is at least m minus plus n over 2. And this implies that E is squeezed between, so either is a short exact sequence where this is m plus n minus r maximum, and this is less than or equal than m plus n over 2. But we know that such sequences are split. And so this means that it's a direct sum. And the last thing I'm going to say is that we can, so this proves our theorem, and this actually easily implies the same theorem for n, rank n bundles. So corollary rank n, so it's a Grothendieck's theorem. Rank n vector bundles on P1 are uniquely of the form O of M1 plus O of Mn, where these numbers are in increasing order. And proof is by induction. Yeah, so we're finishing up. So we just need to do an induction step. So suppose we have this sequence So for n, we already know it's a direct sum. And then suppose we have such an extension. And then, so this means that there is a subbundle E prime inside E, which is preimage of this thing. So E prime J, preimage of the J's thing, which is O of Mj, O of M0. And suppose M0 is maximal possible. Inside E. So we have this thing here. And in particular, M0 is maximal possible here. So this means that M0 is bigger or equal than M0 plus, well, it's not maximal possible, but it's, okay. Yeah, so it's at least M0 plus Mj over 2. So M0 is at least Mj. And this implies that this extension splits. Because it splits for each summon. Okay, so what we see is that, so for example, if you take bond G of SL2, so it has points P0, P1, P2, and so on. So this is O of 0 squared. This is O of 1 plus O of minus 1, O of 2 plus O of minus 2, and so on. And then you see that they get more and more degenerate. So closed sets, so closures of Pi is the union of Pi, Pi plus 1, and so on. And open sets are unions P0, P1, Pj. And so this shows that the points aren't closed, and the closure, for example, of P0 contains everything. Ban SL2 of, yeah, P1, I'm sorry. Yes. Okay, so this shows that this is rather complicated, and will get much more complicated with curves. So next time what I will do is I will talk about cotangent bundle of band G. So we will see that band G, if genus of X is bigger than or equal to 2, then even though this is a stack, it has a big like open set of generic bundles or stable bundles, which is actually a variety and a smooth variety. And we can consider its cotangent bundle and do symplectic geometry on this bundle. In particular, it will carry a canonical, very beautiful and important integrable system called the Hitchin system. And we will construct this system and discuss its integrability. And then we will go to quantizations.
Since we are a little bit over time, maybe all questions and discussions will be during the session. Okay, thank you. Well.
Yeah.
Okay, and lunch will be in building A4, which is the next building in that direction.